to this, the first of 2 tutorials on the subject of indices, which very loosely speaking is the topic of powers of numbers. Now it's quite helpful to break down this topic into 4 separate rules, along with sort of 2 very helpful mathematical statements. So I think in this first tutorial I'll get through about half of that, and then I'll do the other half in a second tutorial. I'm not going to prove these rules, but I'm going to motivate them so that you can get a strong idea of where they come from, so that you don't have to take these things completely on trust from me. So let's first of all consider some symbol A, which we're going to be taking powers of. Let's, for example, think of it raised to the power of 3. What do we really mean by this? What we mean is that symbol, or that quantity A, multiplied by itself 3 times. So this power or index really tells us, and it's an instruction, how many times we should multiply A by itself. Now, the number that the index is being applied to is often called the base. So that's a useful piece of terminology to bear in mind. Now, if we were to have something like a cubed b squared, we have 2 different symbols, 2 different bases here. We can't mix them. And so actually, this is the simplest way in which we can write this product, which stands for a multiplied by itself 3 times, times b multiplied by itself twice. So if you are looking at products involving different bases, do not worry about trying to combine them in some sense. Really, they cannot be expressed in a simpler fashion than what we see here. The point of these 2 tutorials really is considering expressions that involve the same base, but with all sorts of crazy indices going on, and how we simplify that. And the rules that I will show you tell us how to do those simplifications. So let's start with a simple example. Let's imagine that we have a to the 5 multiplied by a to the 3. What does that literally mean? It means a multiplied by itself 5 times, and then multiplied by a cubed, or a multiplied by itself 3 times. And what we can see very simply here is that we have a product of 8 a's, which can be written as a to the power of 8. And so we notice, of course, that 5 plus 3 is 8. The index of the total product can be obtained by adding the indices in the original product. So we have our first rule, let's call it rule number 1, which is that if we have this base raised to a power m, and we multiply it by that same base, it has to be the same base raised to a different power n, then we can write it as a base raised to the power of m plus n. A very important and useful rule. I've motivated where these powers or indices are integers, but in fact this rule holds for any type of number you wish. So m and n can be integers, they can be fractions of integers, rational numbers, they can be irrational numbers, they can be symbols, just as I've written them here. So it's a very useful general rule. Now let's consider a division. Let's consider a to the 5 divided by a to the power of 3. So, okay, I have 5 lots of a on top, and then on the bottom I have 3 lots of a. And now we can bring to bear our knowledge of fractions, that if we have common factors, then we can cancel them out between a numerator and a denominator. So in the denominator here we have 3 factors of a, and we also have 3 factors of a on top. Let me just put an extra times 1 there to make you feel more comfortable, but I'm going to strike out 1 factor of a, 2 factors of a, 3 factors of a, and I'm left with a times a divided by 1, which is just a times a, which is a squared. And you'll notice here that a squared, the 2 as the index there, is 5 take away 3. And so we have a very useful additional rule here, that a to the m divided by a to the n is a to the m minus n. And again, I've motivated this rule with integer powers, but this rule holds whatever the mathematical form of m and n. And you can see, in a sense, it's just related to this first rule. If I was to choose this symbol n to be, say, minus p, then I would just have m minus p here, which is essentially this rule here. Now, let us do one more rule here for this section, and then we'll do the last 3 parts in the second tutorial. So let's instead consider a cubed over a to the 5. Well, I have 3 lots of a on top, and I have now 5 lots of a on the bottom. So again, thinking about fractions and common factors, I can strike out 3 factors of a on the top and the bottom. Let me just multiply the top by 1, again, just to give you a bit of comfort that we're striking out these factors. So I strike out 1 common factor of a, 2 common factors of a, 3 common factors of a, and I'm left with 1 divided by a squared. But what I want to do now is go back to rule 2 and ask, well, what would have happened if I had just put in the number 3 and the number 5 here into rule 2? So rule 2 says that a to the power of 3 divided by a to the power of 5 is a to the 3 take away 5, which is negative 2. And so if I compare the outcome of rule 2 with this simple demonstration, I see that I can connect 1 over the base to a positive power with that same base to a negative power. So 1 over a squared is the same as a to the negative 2, and vice versa. So we have a very helpful expression, which is rule number 3, which is that a to a negative power is to be interpreted as 1 over a to that power, but as a positive. This takes a little bit of getting used to, but it's a very useful rule. And so if you encounter problems where you have indices in the denominator, you're very able to bring them up to the numerator, but just taking the power to be negative. Or conversely, if you have a negative index, you're always free to write that as a positive index, but where the quantity is put into the denominator. So we've covered the first 3 rules of indices. There's one more rule to cover, which I'll do in the next tutorial, along with 2 very helpful sort of expressions that can be derived as special cases of rule number 2. So I hope this has been helpful, and I will see you next time for the second tutorial on indices.